Okay, the bead model explains, if you pursue it a little bit, explains how and why disturbances propagate. And the bead model can lead to the wave equation, which is a partial differential equation that we'll see before too long. The result of the wave equation for a situation like this is a function y of tx of the form sine of pi times, well, sine of some multiple of t plus some multiple of x. Now, the function in the second problem is just given as sine of pi times the quantity t plus 4x. We want to look at this function, which is a function of two variables. It'll have partial derivatives with respect to t and with respect to x, but that comes a little later. We want to look at what this implies. Okay, so if we let t equal 0, we get the function y of 0x, and you can substitute 0 in here. You'll see that you just get sine of 4 pi x. Now, this is just a function of x, so we can figure out its period, various characteristics of the graph of this function. Okay, and this is a sine wave. The period has a property that 4 pi times whatever change in x corresponds to a period has to equal 2 pi, because a period occurs when this quantity here changes by 2 pi. So 4 pi times the period being the change in x that drives this to 2 pi, it gives us the means of understanding and calculating the period without having to resort to a formula that we're likely to mix up. The period then turns out to be 1/2, as we can easily see, and we can check that. If x changes by 1/2, 4 pi x changes by 4 pi times 1/2, which is 2 pi. So we have a sine wave with period 1/2, and we can draw that down here. Here's our x, here's our y. So here's our sine wave. It's got a period of 1/2. The whole cycle begins at the origin, ends on the x-axis at the point 1/2, 0. And we can divide this period into 4 equal parts, so that half the period is 1/4, half of that is 1/8, and we see that let's see if I can make that 8 look a little better. Not sure that helped. We see that sorry, slight interruption in the lab. Anyhow, period's 1/2. We break that into 4 parts so that we have the initial point of the wave, the peak, another point, equilibrium point, another point where the displacement is 0, valley, and back to our original position. And each of those phases takes 1/8 of a unit of x. So there's our graph. Now we're going to look in just a second at what happens if we let t equal something else. As we change t, well, let's just do it. Okay, I'll get another board here. We'll continue. Okay, we're going to let t equal 0.5 and do the same thing. Now, if t is 0.5, then we're going to substitute 0.5 where t was, and we can rearrange this into this form in one manner or another. This intermediate step isn't sacrosanct. There are other ways to get from here to here. Most easily, well, anyway, we get to this point, and we see that our original sine of 4 pi x, the x has been replaced by x plus 1/8. What does that do to our graph? Well, you should think about that. You should understand that, but you might not have thought about it for a while. That shifts the graph 1/8 of a unit to the left. Explanation for that is that x, to get the same value that we would have gotten for sine 4 pi x, x is going to be 1/8 of a unit less. And that'll put this, if x is 1/8 of a unit less, we get the same thing here that we would have gotten for sine 4 pi x. If you think about that, it's the reason for the translation. I don't know that anybody or very many people in a pre-calculus class think that much about the reason. Just learn to use the rule, but the reason is important, because if you forget the rule, you can always reason it out. Anyhow, okay, that's going to be same as a graph of sine of 4 pi x, but shifted 1/8 of a unit to the left. Now I ask the question here, what's the average rate of change of the x position with respect to t, the x position of that sine function? Well, the x position of the graph shifts by -1/8 when t changes by 0.5, so that rate is delta x over delta t, -1/8 over 0.5, which is -1/4. This turns out to be the speed at which the wave modeled by the sine of 4 pi times the quantity t plus 4x, sine of pi times the quantity t plus 4x, our function, models a wave moving to the left at -1/4 of a distance unit per unit of time. If distance is measured in meters, time in seconds, that would be -1/4 of a meter per second. I've sketched two graphs, a graph of sine of 4 pi x, just as before. I haven't labeled the axis, but these are intervals of 1/8 of a unit, as we saw before. And then the graph of sine of 4 pi times x plus 1/8, which is shifted to the left 1/8 of a unit. So that instead of starting the cycle here, we start here at x equals -1/8. Again, these markings corresponding to 1/8 of a unit. And we see then that we have a leftward shift of 1/8 in a delta t of 0.5, which means we have an average velocity of -1/4, the units being whatever our unit of time, our unit of distance is, divided by our unit of time.